All right, so let's move on to series now. This is the meat of this chapter, the real important stuff that we have to focus on for the next couple of weeks until this is over. All right, so you can read the definition there, convergent and divergent series. So I guess first of all, what is a series? Well, you can kind of see what it is. It's just this type of thing here. When you see this notation, specifically the infinity on the top, that's the kind of series that we're going to be dealing with here, infinite series. And I think you might have seen this sigma notation, the summation notation in your Calculus 1 class, maybe when you were talking about summations of indefinite intervals, yeah. So if I hope that you've seen this notation before at least, but you probably haven't seen it with infinity on the top there. Basically what this is, you haven't seen the notation before. It's the big sigma symbol here means that you're adding a bunch of stuff together. This n down here, that's the index, and this is the index that will be changing with every iteration of that index there. Basically, you start at the bottom value, and then you iterate, you go to the next one, and then you put a plus sign between it, and then you go to the next one, you put a plus sign between it. And so you just keep doing that, in this case, all the way to infinity. So these ones just go forever. So this is what it would look like if you wanted to write it out longhand. And there's no way you can write all of them, so you just put plus dot 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 at the end to indicate that that pattern is just going to keep going forever. Okay, so that's really the basic definition of what it is. So this next part here that we're going to talk about is pretty difficult, I think, to wrap your head around at first. So I understand when I first started seeing this stuff, it was like, what are you talking about? It's not easy to kind of get a grip on when you first see it. Nonetheless, we got to talk about it. So what I'm going to write next is, like, when we talk about sequences, really, or by series, what are we really going to be looking for in this class? And so to do that, we have to kind of associate the series with the sequences that we've just been talking about. So with each series, or let's say with any series, there are two sequences that are associated with it. Two different sequences. What are these two sequences? Okay, so the first sequence is the sequence of terms. So let me give you an example. Suppose I give you this sequence here, series, I mean. This is the series, right? Let's just do 1 over n. That's an easy one to deal with. That series, if you start writing out the terms, it's this. It's 1 plus 1/2 plus 1/3 plus 1/4, right? So the result of this is just going to be a bunch of numbers, infinitely many numbers, in fact, added together. So what we're going to be talking about is, well, does that converge and stuff like that? But really, for the purpose of what we're doing right now, that's what it is, right? That's what the series actually is. It's just a bunch of numbers added together. The sequence of terms that are associated with that is this. We usually call that just a sub n, and that's just the list of the terms that would be added together. So it's this. It's 1, 1/2, 1/3, 1/4, etc. Okay, so now, again, this is a little bit subtle, because what is the difference between these two things, right? What is the difference between the series that I wrote and the sequence of terms that is associated with it? Well, the series takes all those terms and does what with them? It adds them all together, right? But the sequence by itself, it's not adding them together. What is it doing? It's just listing them. You see, I just have commas between them, right? So basically, the sequence that's associated with that series is just the list of the terms that are being added together, okay? Not actually adding them. It's just listing them. You see what I'm saying? That's one of the sequences that is associated with any series, with this particular series in this case. What is the other one that is associated with this particular series? This is the one that, I mean, both of them are important, but this is the one that really is going to be the most important for us. That's the sequence of partial sums. That is usually indicated with an S rather than an A, so S sub n rather than A sub n. Using this same example, what is the sequence of partial sums? Again, we usually denote it as Sn. Okay, so if I wanted to say list out Sn, I am actually going to list out Sn here. So what is Sn? Well, sequence of partial sums, right? The first one is going to be called S1. Okay, S1. Well, what's S1? It's basically if you start at 1 and end at 1. Okay, so the first partial sum is just having the lower bound and then stopping at that same number. In other words, it's basically just the first term of the series. So what is that? Well, in this case, it's just 1. The second term, S2, is now going to be if you replace this infinity with a 2. And so I'm going to just say, what's that? What's 1 plus 1/2? What's the first two terms added together? See? And so that's 3/2 in this case. So that means that is my next partial sum, 3/2. Everybody kind of see what's going on? So this is S1. This is S2. What's S3 going to be? Well, again, how do you determine it? You stop at that third one. You would make that 3, and then you would add those 3 together. See? Okay, 11/6, yep. So that's the next term in the sequence of partial sums. And so what would the next one be? Well, the next one would be that one plus the next term in the series. So it would be 1 plus 1/2 plus 1/3 plus 1/4, right? So basically, to get the next one, I just need to add the next term. So 11/6 plus 1/4, 25/12 exactly. And so you can actually write out the sequence of partial sums. So like in general, this is what it would look like. You've got your series here, right? For a particular series, a sub n. Sn, the sequence of partial sums, is going to look like this. It's going to look like a1, a1 plus a2, a1 plus a2 plus a3. You see? Eventually, you're going to reach the nth term of this. Well, what's the nth term going to look like? It's going to be the sum from k equals 1 to n of a sub k. And then it just keeps going after that forever. Now see what that does, right? Does everybody see what this notation represents? And that would be like k starting at 1, right? So that would be the first term. And then plus a2. Where does it end? It ends at the nth term, right? So plus dot 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 plus an, right? And so that, in fact, if you look at the pattern here, right, a1 plus a2 plus 3, that is really the one that goes right there, right? And so that is actually the nth term of the sequence of partial sums. So it turns out that that sequence of partial sums, that's the thing that we're really interested in finding, because that will tell us whether the series diverges or converges. In fact, you can look at it right there on the definition there. It says convergent and divergent series, right? It says if the sequence of partial sums converges to some number, then the series converges. And the limit of that sequence of partial sums is in fact the sum of the series. So again, these things called series are kind of odd beasts, because it seems like when would we ever even possibly get a convergent series other than like adding a bunch of zeros together, right? Like, is it possible to add an infinite number of numbers together and somehow arrive at a finite number? This is kind of that same weirdness that we were seeing with the improper integrals, right? What looked like was probably going to be infinite area turned out that it could actually be finite, right? And so the same thing is happening here. These weird things where you add up an infinite number of numbers, but somehow you get a finite number at the end of that, right? So they're odd things just to begin with, and so now we have to delve even further into this weirdness. See, like, when does it happen when they converge? How do we tell if it converges and stuff like that? All right, so there's two, right away, there's two types of series that are going to be kind of the easiest ones for us to deal with. Easy in that you can usually or almost always find a formula that will tell you what the sum of the series actually is. So I'm going to tell you right now, in general, it's pretty difficult to find the sum of a series, just any series, any infinite series. But that's generally okay, because we often don't need to find the actual sum. Oftentimes it's good enough to get an approximation, as we'll see. And oftentimes all we really care about is, does it converge or not? We don't even really care about what the sum actually is. There's two exceptions to this. In other words, there's two series that you really very easily can find the sum, and that's telescoping series and geometric series. For both of these, we can find the sum pretty easily. Okay, so if you can establish that you're dealing with a telescoping series or you're dealing with a geometric series, well, then you're in good shape, because you can pretty easily find the sum. So let's start with the first example is geometric. So let's start with geometric and then we'll do telescoping even in the other order on the worksheet. So let's do geometric first and then we'll talk about telescoping. Okay, so what are these? These are, again, just a specific type of series that looks like this. When you see a series that looks like this, you know it's geometric. And again, one thing just to also notice about series that's not true about sequences. See how you can start it pretty much anywhere you want it, anywhere you want to? That's just happens to be the case with series. You can begin these things at any number that you want, even negative numbers if you wanted to, but usually we don't do that. With sequences, remember, you have to start at 1. Okay, series though, you don't. You can start at whatever you want. Typically, like for geometric and most of these other ones, we started either at 0 or at 1, usually 0. Okay, so geometric series. You can read about them on the worksheet there, but I am going to go through the little proof of how we end up getting that formula there. So let's think about what the sum of a geometric series might actually be. Let's see if we can figure it out. So notice what the first term would be. It would be AR to the 0 power, right? Which is just A. You get A plus, if n is 1, then you get AR, right? AR. If it's 2, you get AR squared, and so on, right? So this is what they look like. So if you see something like this, you know that is a geometric series. Now, how could we possibly go about finding the sum of such a thing? Well, let's see. So notice, let's do this. What is S sub n? Okay, S sub n. So this is, again, this represents the nth partial sum, okay? So this is the 0th term. 0th term is that one, right? And then the first term, I'm just going to copy what I've already written up there. And then, again, keeping in mind that I am looking at the nth partial sum here, meaning that I'm going to stop when I reach the nth term. Now, since this thing actually starts at 0, the nth term is actually going to end up looking as n minus 1. So we're going to get n minus 2 and then n minus 1. Okay, so everybody kind of see why we're stopping at n minus 1. It's because we're starting at 0. Okay, that's why the nth term actually ends up being n minus 1. Okay, now just notice what else we can do here. If you guys have seen the proof of Gauss method of adding up the first 100 digits, it's kind of like that. So the next thing that we'll do is multiply that by r. Okay, so if I multiply this by r and write it just directly below, and I'm going to line up all the terms that are of the same power, okay? Okay, now in this case, this one will actually end with the nth one, right? Because what did I do? I multiplied it by r, right? So that's going to add 1 to the last term there, and we're going to have the nth power on the last term. All right, now this is the clever part here. And so what the next thing to do is just to notice that you can now add these or subtract these vertically. So I'm just going to put a minus sign here. I'm going to subtract this entire row here. Look what happens when you do that. On the left side, you get Sn minus R Sn, right? But look what you get on the right side. AR minus AR, right? So just vertically subtracting, right? All of these, when I subtract, they're all going to go away, right? Every single one of them is going to go away. All of those end up being 0, right? 0 is all the way. But we're not left with completely 0, right? Because what is not getting canceled? The very first term, right? A, that is not getting canceled. And the last term is also not getting canceled, but that one's being subtracted as well, so you get that. Now look what you can do on the left side here. You can factor out that S sub n, leaving you with 1 minus r. Divide, you get Sn is equal to, okay, now that, then what I just have written here, this is the nth term for the sequence of partial sums, okay? In other words, this little formula here is going to tell me what the nth partial sum is. See what I mean? In other words, if I want to know what the nth partial sum is for a geometric series, I'll just plug in whatever n I happen to be asking for. I can figure out what the 100th term is, or what the 1000th term is, or what the millionth term is, right? But really, for us, the purpose here of knowing this, or the benefit of knowing this, is that if you remember what it says at the top here, what is the limit of this nth partial sum? In other words, what is this? Well, that, according to the very top of 11.2, the limit of the partial sums is the sum of the series itself, right? So basically, if I can figure out what this limit is, then I've figured out the sum of the series. And so really, if I can figure out what that limit is, then we'll be able to find the sum of a series. And I think I forgot an A right there. Okay, so let's think about this. What is this limit going to be? Well, in particular, the only place that we're actually even seeing an n at all, right? This is the limit as n goes to infinity, is right there, right? That's the only occurrence of the n. And if you remember, from the previous section, what is the limit as n goes to infinity of r to the n? Well, it depends on what n is, right? In fact, the a doesn't even matter. We don't even need to bother with that a there. Suppose I just ask that. This depends on what r is, right? And if you look at that previous section, we just saw that that limit is going to be 0 provided that what? Provided that that r value is less than 1. Absolute value is less than 1. Or if you want to write it in longhand, it's like this, right? That limit is 0 provided that r is between -1 and 1. If the r is bigger than 1 or less than -1, then it diverges, or if it's equal to 1, then it just ends up being a constant. But really, for our purposes here, the fact that it's 0 is important, because if it's 0, then that means this thing has to be, that means that term is going to go away. Notice that this equality is true here, provided that what? Provided that this is true about r, okay? So if r is less than 1, it's some fraction between -1 and 1, then you can use this formula to find the exact sum of a geometric series. You see? So here it is. That is the formula for the sum of a geometric series. And that's, again, only true provided that the r value is there. So just to give you a quick example, suppose I asked you, what is the sum? Well, in fact, let's just do one, because we have an example right here, I think. Yeah, 1 over 3 to the n, right? So look at example 1 on the worksheet. It says find the sum of this series, if possible. Okay, now a couple of things just to notice right away. That formula, this is pretty important, works provided what? That we start at 0, right? Starting at 0. In fact, you can see on the worksheet it has to start at 0. This one doesn't start at 0, right? It doesn't. But you can force it to start at 0 pretty easily. So this is the first thing I'll show you. In fact, even before we do that, let me just write it like this. You can always rewrite a fraction where there's just a 1 in the numerator like that, right? Because 1 to the n is just 1, right? So I can write it like that. Notice, why would I want to do that? Because now look, you can clearly see that this is definitely a geometric series, right? A is equal to 1, r is equal to 1/3, and then it matches exactly what we want for a geometric series, right? A r to the n, a r to the n. Okay, everybody see that? So it is definitely a geometric series. R is definitely less than 1, and so that's telling us we can definitely use this formula. Okay, so we're good. The only thing that we have to fix here is that this doesn't start at 1. So that's pretty easy to fix. Like I said, I'm going to just make it start at 0 now. But how did I do that? I lowered this by 1, right? Well, it turns out the way that you can fix it is if you lower this one by 1, then this one has to be raised by 1. Okay, so this one goes down 1, then this one goes up 1. If this one goes down by 2, the bottom one goes down by 2, the top one has to go up by 2. So basically, however many you lower the bottom one by, all the other ends in that formula have to be raised by that same amount, okay? So that's the fix for making it start where you want it to, at 0. Okay, so what did I do? I lowered it by 1. That means I can fix this by raising it by 1. And so I just changed that to n plus 1. But then I still needed to make it match the exact formula for the sum of a geometric series, meaning I don't want an n plus 1 up there, I just want an n up there. Well, that can be fixed by using properties of exponents, right? I can now write this as 1/3 times 1/3 to the n, right? I mean, that's a property of exponents, right? When I have a to the power of n times, or a to the power of n plus m, what is that? That's a to the n, a to the m, right? Everybody with me? So now it's written exactly as I want it, right? It starts at 0. This is the a, this is the r, right? A is 1/3, r is 1/3. So now I've got everything I need, and now I just plug it into the formula, okay? What does the formula say? That's what we had written up here. There's the formula. Oops, I don't need to have a limit on that thing. Shouldn't be a limit on that. should just be that. So that is the formula for the sum of a geometric series. So in this case, again, we identify A as 1/3, so we just put a 1/3 on the top. We identify R as also 1/3, so I just put a 1/3 there. See what I'm doing? Just plugging it into the formula. Now we simplify that. 1/3, the denominator is 1 minus 1/3, that's 2/3, right? And then it's in the denominator, so I can flip it over, multiply by 3/2, and I get 1/2 for the end of this thing. So what is that telling us? Again, that means, again, just putting this all into perspective, that means that if I do this, I have 1/3 to the n, and I think about what those terms are, I would have 1/3 plus 1/9 plus 1/27 plus 1/81, etc., right? And I would just keep going. This would just keep going forever, right? All these numbers added together. Well, what's the sum of all of this stuff? If I add all this stuff together, I actually end up with a finite number, 1/2. Okay. Does that make sense what we're doing here? Any questions? If not, let's talk about telescoping series then. Okay, so telescoping is the other kind, like I said before, it's generally pretty difficult to find the sum of a series. So those geometric ones where we have a formula for it, that's rare to be able to do that, to actually just find what the sum is by using a formula. Telescoping are the other types of series that, in this case, you can't really find a formula, but you can figure out what the sum of the series is. So let's see how this works. And the best way to do this is just to use an example. So I'm going to use example 2 to motivate this. So this is an example of a telescoping series. And just FYI, you can kind of see that these take a very different shape or form than those geometric ones. So generally speaking, you will be able to tell the difference between these two just by looking at them. You won't have to say, oh, is this possibly geometric or is it possibly telescoping? No, I mean, you can see that the form is very different, right? This doesn't have a r to the n. It's got a number over a polynomial. Anyway, the deal with these is that you want to first rewrite the terms of the series. And you do that by our familiar method, partial fraction decomposition. So, and I'll just warn you, in differential equations, you want to take that class, maybe next semester even, you will do even more with partial fractions. They're very important in differential equations for what's called the Laplace transform. I'm going to write this as n plus 1, and then we'll put the n plus 3 as the next term. So partial fraction decomposition, if we hopefully remember how that works, these are not going to be anything near like some of those partial fraction decompositions we had to do back in techniques of integration. These are very simple ones, so don't worry about the actually doing the partial fraction decomposition. These are nothing more than just only linear, single linear terms. That's it. So they should be pretty simple. So here we can let, for example, n be equal to, let's say, -1. And if I do that, I get 2 is equal to 2a, right? So a is equal to 1, right? And then let's let n be equal to -3. And if I do that, then I get 2 is equal to -2b, and so b is equal to -1. Okay? So that's, like I said, hopefully a pretty straightforward partial fraction decomposition. Now I'm going to come back and rewrite this series with its partial fraction decomposition terms instead of the way it was written before. So let's see, a was 1, so I'll have 1 over n plus 1 plus a minus 1 over n plus 3. Okay, so now I've rewritten the terms of the series, and now we're going to try to figure out, again, if we come back up to what we did before with that geometric series, what we were really trying to find is what is that Sn term? What is a formula for the nth partial sum? We're going to do exactly the same thing here. We want to find out what is that Sn term, because that Sn term is all important. If I can establish a formula for Sn, then I can take its limit, and whatever that limit is, that's the sum of the series. Okay. So let's see if we can come up with a formula for Sn for this particular telescoping series. Okay, well, S1 is going to be 1/2 minus 1/4, right?
Yeah.
Now I'm not going to attempt to actually do the subtraction here. I'm just going to leave that as the first term. Okay. Plus, what's the next term? Well, if n is 2 now, what's my next term? 1/3 minus 1/5, right? And I'm just going to keep doing this for a little bit, and then I'll have 1/4 minus 1/6, and so on and so on. I'll just do one more. I think that's probably enough. Okay, now this next part, you have to really kind of think about what is actually happening here. We're trying to come up with a formula for the nth partial sum, right? Now, I can't just keep going with this and just say, oh, it's going to end somewhere, right? We just know it's going to end at the nth term. So what I can do now is say, well, I know there's going to be a bunch of other terms here somewhere. There's going to be a term that follows that fourth one that I just wrote. There's going to be a fifth one after that, but I can't really write all of them. But I can skip over them and then say, okay, well, what's going to be at the very end of this? What is like the third to the last term going to be? In other words, Sn minus 3. What is it? Actually, let's do the second to the last term. What is the second to the last term going to be? It's going to be the term that I get when I replace n with n minus 2. So I'll have an n minus 1 there and an n plus 1 there. So this is the Sn minus 2 term, okay? And then I'm going to have the Sn minus 1 term. And that's going to be 1 over n minus 1 over n plus 2. This is the Sn minus 1 term. And then the very last term that I'm going to get is the nth term, right? That's 1 over n plus 1 minus 1 over n plus 3. So this is the Snth term, you see? So that is, in fact, the last term. That is the last term. So let's see what happens now. Why is this called telescoping? And if you think about what a telescope does, right, if it's fully expanded, it's got, that one eyepiece and then the other end, right? But if you want to put that thing away, what do? You collapse it, right? And so that's kind of the way you want to think of this. Look what happens when we actually write these terms out. There's a minus 1/4 here, but look later on, there's a plus 1/4, right? So that cancels out, right? And then look, there's this minus 1/5 term here, but later on, there's a plus 1/5 term, you see? That's why I didn't want to add these together, because we wouldn't notice that. And then if you think, again, I had to put this plus dot 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 here, because I can't obviously keep going. I mean, I could write out the first 1,000 terms if I wanted to, but I don't really have to. But I know that there is going to be something there, right, in that plus dot dot dot. Well, what do I know for sure? There's going to be a plus 1/6, right, in the next term that I didn't write here, maybe that first dot. There's going to be a plus 1/6 there, right? And it's going to cancel with that minus 1/6, right? And then later on, there's going to be a plus 1/7. It's going to cancel with that one. See? Now, if we come over to the other end here and look at what we've got on the other end, I have this plus 1 over n plus 1 term, right? But look what came 2 terms before it, right? Equal and opposite, right? So those cancel. And by that same logic, this one came 2 terms before it, right? And it canceled. That must mean that there's something that comes two terms before that, right? But again, that's sort of incorporated into that plus dot dot dot. It's there, I just didn't write it. That's going to cancel that term too, right? And very similarly, there's going to be a term 2 terms before that one. Again, in the dot dot dot, it's going to cancel that one, you see? Now, not everything cancels, right? And that's why we call this telescoping, again, because with a telescope, when you collapse it, what still is there? Well, the front of it and the back of it are still there, right? Well, what's on the front of this? 1/2 plus 1/3. Those terms didn't cancel. What's on the other end of this that didn't cancel? 1 over n plus 2 and minus 1 over n plus 3, right? Those terms didn't cancel either. And so what I actually have here is I've got a formula now for the nth term of the sequence of partial sums. And just like we did with the telescoping series, I can now ask, what is the limit of that sequence of partial sums? Well, if you look at what we have here, these terms here, when I take the limit as n goes to infinity, that is going to go to 0. And so is that, right? Both of those terms that have the n's in the denominator are both going to go away. What does that leave me with? Just a number, right? 1/2 plus 1/3, which I believe is 5/6. And so there we go, 5/6. What is that? That's the limit of the sequence of partial sums. Well, by definition, the limit of the sequence of partial sums is, in fact, the sum of the series itself. So what we've just found here is the sum of this telescoping series, the exact sum. I'm going to clear this away and we're going to talk about our first test to see if a series is going to converge or not. All right, so those two series that we just saw, telescoping and geometric, right? Those ones we can very easily tell if they converge or not because we just have to use either the formula for the geometric series or just look at the R value and say, well, it's bigger than 1, it's going to diverge. The telescoping ones are pretty much always going to converge. So in general, though, all other types of series, difficult to find the sum of the series. But usually it's not that difficult to tell if it's going to converge or not. So that's really going to be the focus of the next couple of weeks here. How do we tell if a series is going to converge or not? How do we determine whether or not a series converges? And that is often the only question we need to ask. Does it converge? We don't really even need to know what it converges to. We just need to know if it converges. And so that is the focus, like I say, of the rest of, or a good chunk of what we're going to do in the next couple of weeks. So we have all these tests that help us to determine whether a series converges or not. Okay, so we just use tests for convergence. So we need to know about these tests. And we have our very first test right here. It's called the nth term test. So this is test number 1, nth term test, or sometimes called the divergence test. Now this one, given the name, that's the one I usually call it, divergence test. Given the name, you can kind of tell this one actually is sort of a quasi-test for convergence. It doesn't really tell us if it converges. All it will do is it tells us that it diverges, okay? And so you can see the divergence test is right there. And in fact, if you are familiar with logic, you'll see that that limit of the nth term of a convergence series is just a restatement of the divergence test. They are in fact the same thing. So let me just write the divergence test here. If the limit as n goes to infinity of a sub n, and remember what a sub n is? A sub n is the terms, the sequence of terms of the series. If this limit is not 0, then the series diverges. So that's a really easy test. In fact, I usually recommend just using this test right away, because if this test, if you can show that that limit is not 0, then you're done. You just know that this thing is going to diverge. Okay. I usually go through this whole thing about some logic. I told you that the thing at the bottom of the page for 11.4, the first page, sorry, for 11.2, that theorem, limit of the nth term of a convergent series, is exactly the same as the divergence test. They are just restatements of the exact same thing. And in fact, if you are familiar with logic, the divergence test is what's called the contrapositive of the limit of the nth term of a convergent series. Let's go ahead and do that third example there. So this is, I just put a 1 there as in saying that's the first test. We're going to have a lot more tests to do. This is just the easiest one and the first one. It's the easiest one because, look, I'll show you how easy it is. The question is, does this particular series converge or not, right? That's the question. If, in other words, if I were to add up all the terms of this particular series, would it go to infinity or would it go to a finite number? So the nth term test just tells me all I have to do is look at the terms, in other words, the stuff that doesn't have the summation on it, and find that limit. And what is this limit? Well, hopefully we can see that that limit is just 1/2, exactly, good. And then all that we have to do is say, well, that is not 0, right? 1/2 is definitely not 0, right? Easy enough. And so by the divergence test, look what the divergence test just said. If the limit isn't 0, then what? Then the series diverges. So that's it. So this particular series diverges by the divergence test. And I usually abbreviate these. We have a bunch of them, so we'll start abbreviating them. Just real quick, I guess I probably should say a little bit of something about that limit of the nth term. So if you look at the bottom, that theorem at the bottom of the page, it says if the series converges, then the limit is 0, the limit of the terms is 0. This is why the divergence test works, because the divergence test is just a restatement of this particular theorem. Why is this true, though? Why do you think it has to be true that the limit of the terms has to be 0? Well, think about it. If it's not 0, suppose that it's not 0. Suppose you have this. In fact, even make it easier here. Suppose it's just 1. Let's just say it's equal to 1. Then let's think about what the nth partial sums are going to look like, right? So then when you start looking at the nth partial sums, what are they going to look like? And what is the sequence of partial sums going to actually start looking like? Well, you're going to have, let's see, at first you're going to have what, S1, right? And then S2, and then S3, and so on. But eventually, you're going to come way out here, and you're going to have these terms out here, right? Well, if the limit is not 0, if it's 1 out here, then what's going to happen? You're going to have a term out here where you're going to have some number, right? You're going to have some number. And then what's going to be true about that? Well, you're going to be adding on 1 every time, right? Because the limit here is 1, or something really close to 1, right? It's not going to actually be 1, but it's going to be really close to 1 because we're way out here, right? Like say this is the millionth term, right? You're way out here in the millionth term, or 10 millionth or whatever. Then I'm going to have some number here, but since the limit of this thing here is not 0, so say it's 1 is what I'm saying there, then that means that I'm going to be really close to 1 when I'm out here, right? I'm going to be out here on a term that's really close to 1. And I'm going to have some number, and I'm going to be adding a number really close to 1. And then I'm going to have on my next term another number, and then I'm going to be adding something really close to 1, right? Well, is there any way that could possibly converge, right? Like if every single time I keep adding 1 to it, way out in the billionth or trillionth term, there's no way it can possibly converge to anything, right? Because I'm continually adding 1 more to it. However, if this limit is 0, suppose it is 0, then what's going to happen on these terms way out here? What am I going to be adding to it? Not a number really close to 1, but a number really close to 0 instead, right? Everybody kind of see where I'm going with this? If I'm adding a number really close to 0, then I have a chance for it to converge, right? But if it's anything other than 0, what's going to happen on these terms way out here? I'm going to be adding whatever that limit is, or a number really close to that thing. And there's no way it can possibly converge. Okay? So I'm trying to give you a little bit of reasoning about why this actually works without actually going through a formal mathematical proof about it. Okay, so let's go on to that example 3b there. Again, the question here is simply, does this thing converge? Okay, so in this case, again, the question is just, does this converge or not? So I'm going to attempt the divergence test. And again, the divergence test just tells me that I need to look at the terms of the sequence. Sorry, the terms of the series. So that. And then on that bottom one, I'm actually going to go ahead and rewrite it as 2 times 2 to the n. Again, remember, properties of exponents, we really have to be very up on those for this type of thing. Now, this limit, how do I find this limit? Well, it looks like L'Hopital's rule is probably the best way because this does give us an infinity over infinity situation. So we'll just use L'Hopital's rule to find it. The derivative of 2 to the n is 2 to the n, ln2, and then the derivative of 1 is just 0, so that's going to go away. Denominator, I'm going to have 2 times 2 to the n ln2. Now notice that I just get a bunch of cancellation except for that 2 in the denominator, so there we go, I get 1/2. And so again, I get a 1/2 limit, which again is not 0. And so again, what if you were thinking about like listing out the terms of Sn, once I get out to those billionth or trillionth terms, every single time I'm going to be adding a number really close to 1/2. So there's no way it's going to converge. And so diverge by divergence test, or nth term test. You'll often see it called that as well. All right, so that's the easiest test. All you got to do is just take a limit of the terms of the series. If that limit is not 0, you're done. You just say it diverged. If it does come out 0, well, again, this thing is called the divergence test. All it tells you is divergence. If you do get a limit of 0, you can't make any conclusion at all. It may converge and it may not, and then you have to do some other test, which we'll see or next time. All right, we have about 8 minutes, and that I think is about enough time to show this cool next problem. Let's just do that one real quick and we'll call it a day. So this is like the first application of series that we're going to see. And it's kind of a simple little application, but it is kind of cool, I think. It allows us to write repeating decimals as fractions. In other words, it allows infinite series are one method. There's other ways to do it, but it's one method to find the fraction representation of repeating decimals, okay? So we're going to use an infinite series to express this as a fraction. Okay, how do we do that? What we need to notice is that this is the same as 0.46 repeating, right, over and over and over again forever. And so just notice that we could, if we wanted to, we could express this as 0.46 plus 0.0046 plus 0.00006, right? We could just keep going like that forever, right? Everybody see how that works? Is that believable that you can do that, right? That just produces all the 4 6s where they need to be, right? If you just add them all together. Well, notice that that can be written further as 46 over 100, right? And this can be written as 46 over 10,000. And this can be written as 46 over 4 zeros. I need 6 zeros now, a million, I guess. And I can just keep doing that if I wanted to. Now, notice that you can factor out a 46 over 100. When you do that, what are you left with? 1 plus, I took out the 46, so I'm just going to be left with 1, and I took out the 100, so I'm going to have 100 left, I guess, and then I'm going to have 1 over 10,000, etc. And this, again, just keeps going forever, right? This is an infinite series here. Notice now that I can rewrite this a little bit better. I can write this as 46 over 100. Now that can be written in summation notation. I can start this n equals 0, and I can write this as 1 over 100 to the nth power. Everybody see that? Again, just think about what would happen if you let n be 0. Then you would get the 1, right? What if n is 1? Then you get the 1 over 100. N is 2, you get the 1 over 10,000, etc., etc., right? Well, look at this. This is now a geometric series, right? This is our A. This is our R, right? R is 1 over 100. A is 46 over 100. So this is, in fact, a geometric series. And it's exactly the way that we want it because it starts at 0. So I can now use the formula for the sum of a geometric series, which, if you remember, is A over 1 minus R. A is 46 over 100. 1 minus R, 1 minus 1 over 100. So then I can rewrite this as 46 over 100 times, since this is in the denominator, I'll have 1 minus 1 over, that's 99 over 100. It's in the denominator, so I can flip it over and get 100 over 99. And look what happens. Those 100s cancel, and what am I left with? 46 over 99. And so if you have your calculator and you want to just verify this, put 46 over 99 in it. And what do you get? You get 464646 repeating forever. See? Kind of cool, huh? You can do this with any repeating decimal. Change it into a fraction like this.